Very good afternoon to all distinguished speakers, professors, researchers, and students and participants. I'm Dr. Debashis Panda, convener of the program. Heartily welcome you all in this international webinar series on novel materials and devices for supercomputing 2020, IWNMDS 20, organized by Department of Physics, National Institute of Science and Technology, Berhampur. At the time when the entire world is suffered from COVID-19 pandemic, to refresh our mind and boost up knowledge, NIST made this platform where 6 eminent scientists from the top-notch institutions and industries of the world accepted our request and agreed to share their latest findings with all of us. I'm personally and NIST is very much thankful to them to make their time from their busy schedule. More than 250 participants have been registered from Europe, USA, Taiwan, IITs, NITs, etc. and eagerly waiting for this webinar. We have 6 distinguished lectures in 6 consecutive days by considering your work from home schedule and classes by 6 eminent scientists from top-notch institutions and industries at the same time at 4:30 p.m. except the last talk which is arranged at 11 a.m. Indian Standard Time at Sunday as distributed to you. To attend the whole series, you all please use the same link. A feedback link will be provided in between the talk in chat box. Kindly send the feedback as soon as possible. Certificate will be provided after getting feedback only. All are requested to write your queries to speaker about the talk in chat box only. Before starting today's talk by our distinguished speaker, Dr. Joao Ventura, I'd like to give you a short introduction about our institute. The National Institute of Science and Technology, famously known as NIST, was established in the year 1996 by a group of academicians and technocrats educated in the top institutions of India and abroad under SM Charitable Educational Trust, where Professor Sangram Mudali is the founder, secretary, and administrative head till date. This is the first NRI educational venture in the state of Odisha and southern Odisha, keeping true to its core value, mission, and vision. NIST has become a top-notch institute in the state and country since establishment. I'm highlighting some important ranking and accreditation only. NIST is an autonomous institution accredited by UGC and accredited by NAC and NBA. Ranked 69th by NIRF, MHRD Government of India, and first among all engineering colleges under affiliated University of BPUT in 216. NIST is ranked among top 100 colleges of the country by DataQuest and Outlook. BPUT students have ranked NIST as #1 engineering institute among 100 plus engineering colleges of Odisha through public voting. NIST has backed with a prestigious e-Odisha and e-India award under the category of Best Teaching Learning. It has signed MOU for research collaboration with National Taiwan University, University of Electrocommunication, Japan, Drexel University, USA, NJIT, USA, Stanford University, USA, IITs, which include Kharagpur, Delhi, Mumbai, almost all top IITs, Osmania University, and many more. I know all of you are waiting for the talk only. Just giving a short introduction about the speaker before starting the talk. Dr. Joao Ventura, Vice President of Institute of Physics of Materials of the University of Porto, that is short from IFIMUP, obtained his PhD degree from University of Porto in 2006. In 2008, he became a senior researcher at the Institute of Physics of Materials of the University of Porto and an invited speaker professor at the University of Porto. In 2012, he was elected president of IFIMUP and appointed member of the Executive Commission of the Associate Laboratory Institute of Nanoscience and Technology. In this role, he collaborated in the implementation of the new 200 meter square ISO 6, ISO 7 clean room, now serving the University of Porto, of which he is now the vice director. Currently, as a vice president of IFIMUP, he leads the area of nanoelectronics and energy harvesting material, that focuses on memory-based neuromorphic applications and advanced triboelectric nanogenerators that has been attracting several prizes, including from the European Space Agency and Repsol. He co-authored several books, one book, 7 book chapters, a number of patents, 165 reputed international journal publication, which includes Nature Nanotechnology, Nanoenergy, PRL, Journal of Material Chemistry, and many more. And so many things he has done. If I like to speak in this short span, it will take 1 week for this his biodata. Sorry, I cannot spend that much time. Since we don't have this much time and we are eagerly waiting to listen his exciting talk, with this short introduction, I like to request Dr. Joao Ventura to deliver his talk on triboelectric nanogenerators from fundamental concepts to applications in harsh environments. And transferring the screen to Dr. Joao. Please, Dr. Joao.
Thank you, Panda. Thank you all for being here. It is a pleasure. I would like to thank Professor Panda first for inviting me to give this lecture here today. I hope you enjoy it. It's on a new topic that is very, very interesting at the moment, so on triboelectric nanogenerators. And I'll go from the fundamental concepts of these new energy harvester devices and their applications, particularly in harsh environments, which is the focus of our research on last year. So we all know that energy is generated typically on a large scale, either from windmills, from light with photovoltaic panels, or by water, taking advantage of the potential energy of water on hydro dams. But nowadays there are other energy sources that you can take advantages of, such as temperature, electromagnetic waves or radiation, and vibrations. So these different energies that are available at our environment, they give rise. They can be harvested using different devices. So typically RF coils for electromagnetic waves, Peltiers using Peltier effect from temperature gradients, or the most commonly used for vibrations or more generally mechanical motions, piezoelectric materials can be used for that. And this gives rise to small-scale electrical energy generation using any of these 3 devices. And these are the typical outputs that you get from these energy harvesters. So photovoltaics has the logical power output density that you have on this scale. So you get something like 10 milliwatts per centimeter square, and you can go down on the power scale down to 1 nanowatt per centimeter square if you take advantage of vibrations or general movements. So the question is, why do we need such a diversity of power scales, and what is this low power scales levels useful for? And the answer is 2. So we have 2 reasons for this. The first is that these energy harvesters, they are becoming more capable. So they are nowadays we are getting more energy out of these small devices that can get small powers. The other reason is that the electronics that we currently use nowadays, they are using less and less power. So as they become less power consumption, we can get these small-scale energy harvesters to feed our electronic gadgets. And if you look at this graph here, you get tens of watts of powers. You can get laptops or tablets or our mobile phone nowadays, but you get things that are running nowadays on the nanowatts, microwatts, or milliwatts power scale. And this is where you want your energy harvesters to work on to feed these small consumption devices. For example, if you go into 10 milliwatts, you already have wireless networks that operate on this range. So you can power a wireless network that sends signals from a sensor anywhere with just 10 milliwatts of power. And this is what you get, for example, for a temperature, for a Peltier device on a temperature gradient. Nowadays, today I will talk about a new energy harvesting technology that is appeared, that is bridging this gap between low and high power energy generation. And I'll be talking about triboelectric nanogenerators. They rely on the contact electrification and on electrostatic induction. So I'll give you a little bit on the fundamentals of this. Then I'll show how the materials can be changed and enhanced to get higher powers from our devices. And then I'll talk briefly about 4 applications that we have been studying. So we have integrated our devices on footwear, on using water flow to generate electrical energy, and then the 2 most recent applications that we have been pursuing, which is the oil and gas energy to harvest energy from the ocean from wave energy. Then I'll show my brief conclusions. So a triboelectric nanogenerator has appeared just a few years ago in 2013, and the power density that it provides has increased very rapidly. And nowadays you can get something like 500 watts per meter square or 500 milliwatts per centimeter square, which is already comparable to photovoltaics. The efficiency of this energy conversion is also very high. So starting from around 10%, nowadays it's higher than 80% of energy conversion efficiency. So these are devices that can get you a high power with a high energy efficiency conversion. They have higher powers typically than piezoelectrics and thermoelectrics, so this is a big advantage. But they also are very simple to fabricate, and they are very simple in their working mechanisms. And there is a wide range of materials that you can use to fabricate these triboelectric generators, and that you can choose for your particular application. And they use a combination of the contact electrification and electrostatic induction on their working mechanism. So how does this work basically? You typically on these triboelectric generators, you have 2 insulating materials. And if you consider one of these, they have typically 1 fixed ion and mobile counter ions. And if you put one of the materials in contact with the other, either in contact in horizontal direction or in sliding, one ion can be captured by the other material. And when you separate the materials, you have charge separation. And the materials, they become electrically charged. So you get one negative charged material, one positive charge material, and you can choose the materials from what is called the triboelectric series. So this is known for over 100 or 200 years, and this series orders materials according to their ability to become negatively charged, like in this case, so they capture electrons, or positively charged, in meaning that they release electrons when in contact with other material. And so typical materials you can find and use are nylon. Okay, this is a material that is very used when you do these devices. PMMA, so these are polymers typically on this side. And on the other side, you get Teflon, which is also very negatively charged, polystyrene, or PET. Okay, and then you have in the middle, typically metals which do not transfer charges, so they don't become electrically charged in a large amount. So what you want is to contact very highly positive materials with very highly negative materials, with very highly negative materials, positive materials, and you get the most charge that is transferred between the 2. And when you have this charge transfer now, what you can do is you rely on electrostatic induction to generate an electrical current. So you put 2 metallic electrodes on the backside of your insulators or your polymers. These metallic electrodes, because the polymer is charged, they redistribute their charges on the surface. So the negative triboelectric material will induce positive charges on the surface of the metal, and the positive charge dielectrics will induce negative charges at the surface with the dielectrics. As you have this, what you can do now is move one relative to the other. And as you move, you neutralize the charges and you also neutralize the redistribution of charges on the metallic electrode. If you now connect a resistance between these two materials, what happens is that as they come closer, the current will flow from one electrode to the other. And as they move backwards, the current will flow again and the charge redistribution will appear. So you have the possibility now that you have this electrostatic induction, you have now the possibility to drive charges through an external circuit. If you join the two things, so contact electrification that gives you the charges on the surface and the charged materials, with electrostatic induction that gives you the possibility to have the charge flowing through the external circuit, you have a triboelectric nanogenerator. And this has been developing very fast since 2013, and there's a whole range of applications that you can get from these devices. So the most typical is energy harvester, but you can use it as active sensors. You can use it as self-power systems. They have already been demonstrated for implantable devices, electronic schemes, or inflexible electronics. So the range of applications is extremely large for these materials and for these triboelectric nanogenerators. They work in four basic modes. The most common is this vertical contact separation mode, where your two materials, they come in contact in the vertical direction. So they come in contact via a mechanical motion, they come out of contact, and this is repeated cyclically so that you have current flowing through the external circuit. You also have this contact sliding mode where the two materials, they slide on one another, and so the same phenomena basically appears. As the material goes away from the other, it flows a charge through the metallic electrodes. Then you have two different modes of operation that rely on a single electrode, and in this case you ground one of the electrodes, and then you have the other material coming in contact with the grounded electrode. This is important, for example, if you want touch screens or touchable electronics, where your ground electrode is the screen, and your material that comes and goes from contact with the grounded electrode is, for example, your finger, like in this figure. And you get this freestanding triboelectric layer mode, where you have two electrodes connected to one another, and a third material that goes sliding from one side to the other. So using these four basic modes of operation, you can get a lot of applications out of this, and so the versatility on these triboelectric materials is extremely high. Now I'll go a little bit into our results and show you what we have been doing on different things. So to start, I'll show you on what we can do to change the materials and the surfaces to enhance the triboelectric effect. Before that, I'll show you how we have to measure these things. So imagine this: on one side there is one triboelectric material, on the other there is the other, so a positive and a negative. They two come in contact. On our triboelectric testing system, we use an hydraulic pump. And as they come in contact, you have a positive peak. As they come out of contact, you have this negative peak. And this is repeated cyclically until you measure it a given number of times. And you obtain something like this, so a voltage as a function of time. And you get three basic quantities that you want. The open circuit voltage, so when the two triboelectric electrodes are on open circuit and you measure it directly on an oscilloscope and an ammeter. You have the short circuit current, where you put a shunt current, a shunt resistance between the two electrodes, and you measure the current that comes out of the device. And you vary then this load resistance that you put between the two metallic electrodes. And you get the near short condition, where you have a very high current and a very low voltage. You have the open circuit condition, where you have a very high voltage and a very low current. And you have a transition between the two, where the current goes from high to zero and the voltage goes from zero to high. Multiplying these two quantities, you get the power, okay? And you get the power as a function of the load resistance. Typically, it looks like this. So it has a maximum at a given load resistance, which is the internal impedance of your device. And this is the working point that you want to operate on. And this gives you the maximum power also, which is the effective figure of merit of these generators. And so now you have a standard way to measure this, and you want to change your materials to see how you can improve the efficiency of the energy generation. And you have two strategies to increase these power outputs. The first is you change the surface tribal electrification. So you change the number of surface charges that you can get on a given material. And this can be done by changing the dielectric permittivity, because the surface charge is directly related to the dielectric permittivity, just like in a capacitor. The second is that you can increase the effective area. So you can see here, for example, the short circuit current depends linearly on the current. And here is an example where you can change the contact area by just changing the pressure or the force that you applied on these nanopyramids-like structures, and and you get an increase of the contact area by the increase of the force, which relates to an increase of the power that you get from your devices. What we have done is we have done PDMS doping with the nanoparticles of silicon oxide. So we have changed the diameters from 22 nanometers to 360 nanometers, and we have changed the concentration of the amount of nanoparticles of silica that you put inside your PDMS material. And this is typically what you have. So there is a maximum of the electrical power, being the current, voltage, or even the power density. You have a maximum as a function of the concentration, typically around 5 to 10%, and this is related to the ability that you have for the material to distribute these nanoparticles inside the polymer. As soon as these nanoparticles come to the surface, you stop having an increase of the power output, and then you have an output decrease. So if you change just the concentration a little bit by 5% of this using nanoparticles of silica, you can get a 56-time increase on the power density that you obtain. It also depends on the nanoparticle diameter. So the smaller the nanoparticles, they have higher. You can get higher output voltages from smaller by doping the PDMS material with smaller nanoparticles. And we believe that this is related with the differences in the dielectric constant of these nanoparticles as the size goes down. You can also do surface texturing, so you can change the surface of your material by different mechanisms. One very simple method is to use nanoporous aluminum templates. These are templates that you can get just by anodizing aluminum into an aluminum oxide. And if you do it right, you can come out with these small dimples on the surface of aluminum, and they can have nano-size features. You can go from 30 nanometers to 500 nanometers very easily. And you can also use microlithography silicon molds, okay? And you can go from something that is on the nanometer scale to something that is on the micrometer scale, and see what happens on this multi-scale arrangement. This is just an example. So the output voltage that you get as a function of time for different structures. So for PDMS, simple PDMS films that are flat with the silicon template that has micrometers features, and the aluminum template that has nanometer features. And what you get is typically a 2 times increase in the output power just by changing the surface of your material, of your triboelectric material. And interestingly, the output voltage that you gain does not relate a lot with the size of your feature. So there is a minimum size that you need to do to get the maximum output increase available. Now that we have the materials, we have the testing system, we can integrate all of this on different applications. I'll start with footwear. This was one of the first things that we have done. So I'll go fast on these first applications so that I can focus on the ones that I think are more interesting at the end. So we all know that while we are walking, we are putting pressure on our foot, and particularly on the heel. So if you go look at the footwear, typically you have something like 7 by 3.5 centimeters square available on the back side, and we want to take advantage of this area to try to make a generator that can harvest your energy in walking. So with this area, we can put a triboelectric nanogenerator there. This is what we have done. We have optimized the configuration that you can put inside, not only the size, but what can we do with these materials. So this is very simple, a structure that looks like this. And here is one of the triboelectric materials. In this case, is Teflon. On the other side is nylon. You have the 2 electrodes on the top and at the bottom. The other structures are similar, but instead of doing these 2 parallel plate structures, you can have an arced structure, or you can have a zigzag structure like this, where you can put multiple steps. So we have optimized this assembling, and what we found is that the parallel plates are typically the best for this particular application. So we have changed the force. They are linear with the force. This can be important if you want a sensor, and we will talk a little bit on this before. But the 3 of them are linear, but then after this we have focused on the parallel plates because it's the one that gives you the higher output power. And you can also change the number of pairs that you can put there. So we went from 1 to 6. I'll show you here some of the results. The thing is that if you increase the number of pairs from 1 to 4, you increase continuously the output power that you get, and you go up to 90 volts and 120 micro amps of current. But after a given value, in this case 4 tribo pairs, the output doesn't increase more because the pressure that you put on the structure is not enough to make all of it to come into contact. This is the power. It confirms what I'm saying. So the maximum power is 4 watt per square meter, and you have it for 4 and 5 pairs of this configuration. This is how it looks like. You have someone that is stepping his foot on the floor, and you have these 3 LEDs that are being lighted by the triboelectric generator that is inside. So to increase this power that we are obtaining, we did an hybrid nanogenerator where we have the triboelectrics at the bottom. Then we put zinc oxide nanowires to do a piezoelectric nanogenerator on top. And we also added an electromagnetic generator with a coil and a magnet on these 3 structures. This is what you have. So the electromagnetic generates the higher power here at the lowest resistance. The triboelectric is at a higher resistance, and the piezoelectric is the one that gives you the smallest power and the smallest output voltage. If you now charge this, if you now charge a capacitor with these structures, what you have is that, and this is why we should consider all of this hybridization. If you have only the piezoelectric, you don't charge the capacitor at all. If you have the electromagnetic, you charge it very fastly, but then it saturates because the output voltage that you get from the electromagnetic generator is very small. If you have the triboelectric, you have basically a linear increase of the voltage at the capacitor. But if you use the hybrid generator that we have done, you have a very increase coming from the electromagnetic generator at the beginning, and then you have the steady increase that comes out of the triboelectric generator at a later stage. And this gives you a 20% increase in the charging efficiency. So we have integrated this in footwear, and this was at the table setup that we have. This is already on the shoe, and you get more or less the same behavior, and you can charge different capacitors at already integrated on a shoe, and this can be used to then charge some sensor or other electronic gadget. So now that we have these structures, we know that we have seen that they can be used as sensors because they have a linear dependence on the force. And so what we did is integrated this on 4 different places on a footwear, and see how we can integrate this as self-power sensors. This is how it operates. This is someone that is running. This is electronic boards that we have to take out the output voltages from, in this case, 9 up to 9 different sensors that are integrated on the footwear. So if you go back to 4, this is what you have at different places of the shoe. So here you have a high voltage. Here you have almost 0 because the pressure is very low. Here is where you can generate the highest voltage. This is just by walking, and again the force, the output voltage is linear with the force. If you go into running mode, then the output voltages are much larger, and you can sense not only the force but also the velocity that someone is running. This is just an example where you have 9 sensors integrated all over the footwear, and the differences that you have depending on the speed that you are walking with. So at a low speed you get 0.8 kilometers per hour. You have very small output voltage, but then this increase as you increase also the velocity of your walking. Another thing that we have done is using these triboelectric generators as a triboelectric turbine to take advantage of water flow motion. And we want to do this for smart water grid applications. So we have been collaborating with the waters of Porto in integrating this in a water pipe that they have and that they want to sensorize to give them information on the quality of water in the city of Porto. So what we have developed is a sort of a turbine, whereas water flows through the turbine. This makes this shaft move here at the top, and as the shaft moves, there are 2 materials that come in contact as this rotates. And this is the construction of the prototype that is now available. So this is how it works. Water is moving here. The 2 materials touch, and as they touch, they can light up these LEDs that we have here. These are about 100 LEDs that can be lightened up just by this water motion passing through our turbine. This is the operation principle. As this rotates, one of the materials, in this case is Teflon, comes into contact with the nylon. As it contacts, there is charge generated at the surfaces. They slide on one another, and as they slide, the electrical charge will move from one of the electrodes into the other. And as they come apart, then you have again the redistribution of charges on the metallic electrodes, and current will flow on the other way when the opposite happens. So we have optimized also this work. We have studied as a function of water flow and for different number of plates that you have on the turbine. And as the number of plates increases, you typically have a decrease of the voltage that is generated because you need more power a larger pressure to induce the same type of movement. But as water flow increases, the voltage also increases, and then it saturates above about 30 liters per meter. The same happens for the current, where you have an increase and then a saturation. And of course, the power will get the same behavior because it's just a multiplication of the two. You also have a difference in the frequency as the water flow changes. And this shows you exactly that the frequency is smaller for the higher number of plates, because exactly you have more friction on your system, and then you will decrease the frequency of the motion. This is what you can charge with, so you can use this to charge very fastly a capacitor, and then you can power, for example, a humidity and temperature sensor that you can have integrated on a smart water grid. Okay, so I'll be talking a little bit about this. This is something that we are doing just now. In fact, tomorrow we'll have experiments on this subject. So we have worked for a couple of years on the oil and gas sector. So this is a very harsh and corrosive environment. This is crude oil that is being driven out of a crude well, okay, an extraction well. These are typically work at very high temperatures, up to 150 degrees, and they work at very high pressures. So at about 800 bar, which is typically the pressure that you have at the bottom of the ocean. And so these are very harsh environments, and they are very difficult to have materials that work on these places. And what people in the oil and gas sector now want is to have monitoring systems on their extraction wells. They nowadays rely on batteries, and so this is very dangerous because batteries, they typically explode in these environments, so they have to be very carefully. Or they have very high demanding in terms of maintenance because they have to replace these batteries very periodically. And why do they want these monitoring systems? Well, they want to avoid things like the Deepwater Horizon, where a lack of security has led to one of the largest accidents in the oil and gas industry history. So the solution is local power generation. So what we want to do is to locally generate the electrical power that is needed to fit sensors at the bottom of the extraction well. And our idea is to use the flow of the crude oil that is passing through the pipe to generate energy using our triboelectric generators. The things that these generators have to have is that they cannot obstruct the stream. This leads to pressure losses, and this is something that the industry doesn't have. They have to be very light and small because they have to fit this small pipe inside this small pipe, and they have to be durable because they have to resist these high temperatures, these high pressures, and the flow of the fluid that is coming out. And so what we did is we went to Repsol in Madrid. Repsol is a very big company that has several extraction wells around the world, and they have facilities for these high pressure measurements. So we went up to 1500 psis and to 200 degrees Celsius to see if our generators work on this. So the setup is very peculiar. They have a high pressure and temperature container, which is here. And what they do is they fill it with crude. And after being filled, if you want to increase the pressure, what they do is they heat up the system. So as the temperature increases, the pressure inside also increases. The problem is that with these things, you cannot vary the pressure and the temperature independently. So as you increase the temperature, the pressure will also increase, and vice versa. And this is how the system behaves. So as a function of time, you increase the temperature in black here, and the pressure with a small lag will also increase up to its maximum value. And then you can have a stable region where the temperature is constant. And then as you start decreasing the temperature, the pressure will also increase. So you cannot separate the two things independently. And this can be a problem if you want to determine what is happening on your devices. Also, the container here is closed, so you do not have the possibility, or you do not have an easy possibility to have a motion. So we had to come out with a new method to induce this mechanical motion inside this container. And what we did is to have a triboelectric generator like this with a rolling sphere on top. And as the rolling sphere makes weight on the two materials, these two materials come in contact and they generate electrical energy. So we put this inside our tube with the crude inside. And this is an example of how it is going to work. So as you move the tube inside filled with crude inside, the spheres will move and you get an output voltage being generated. This is the pressure container that we have used. This is our device here on a Teflon plate. And this is the high pressure bottle system that we have used at Repsol. So the bottle is here, the heater is outside, and therefore the leg with the pressure. You have a thermocouple here to measure the temperature outside. And what we do is you move the container. As you move the container, the sphere will roll, and as the sphere rolls, you have an output voltage inside. This is an example of one of the experiments that we have done. So the container can move back and forth. As it moves back and forth, the spheres will roll. As the spheres roll, energy is generated by the two triboelectric materials coming into contact with one another. So if you study what happens in crude oil, this is the experiment. So you can go from 70 bars to 830 bars, and the power, the output voltage in this case, decreases as you increase the pressure. Okay. Remember that as you increase the pressure, the temperature is also increasing, and you can plot the output voltage as a function of the pressure. And here is what the graph looks like. So for a given pressure, the temperature is also changing. It goes from 50 to 120 degrees. And the question is, of course, what happens, what is making this decrease occur, if it is the pressure or the temperature that is varying. So we have also shown that we can take, that we can charge different capacitors at different pressures. So we can go from 200 bars at 60 degrees up to 800 bars at 120 degrees, and you can still charge capacitors at these high pressures and these high voltages. But at the end, your device looks like this. So this is your container with the crude oil, and this is how everything looks at the end. These are the rolling spheres. This is your triboelectric materials, and everything else is crude oil, just all over the place. But the device, even after all of these tests, it was stable for 4 hours at these very harsh conditions. We did another experiment to try to discriminate what is happening from the pressure from the temperature, and we did this with methane. So this is also a gas that comes out of the extraction wells. And in this case, because you have a gas, you can separate the temperature from the pressure. So in this case, we decrease the pressure, and as you decrease the pressure, the output voltage comes down a little, but it doesn't change very much. If you increase the temperature, now you will have a very high effect. So if you increase the temperature, the materials will degrade very fastly at temperatures higher than 100 degrees. And so the temperature is the most important factor in reducing the output voltage that you get out of triboelectric nanogenerators in these environments. And so you need to come out with different materials that can avoid this effect. So just tomorrow we'll have dynamic tests at Norway at high pressures, but we have built here in Porto a small setup that can give us dynamic conditions in crude oil. So we have a pump for oil that makes this that can put oil through these pipes, and then it comes out, and this is all a closed loop circuit. And here inside this point, we can put your triboelectric nanogenerator and see what comes out as a function of the dynamics of the flow. So we have used oil inside, and we can go up to 50 degrees Celsius and at 55 liters per minute, but at room pressure. And now we are doing tests up to 200 bar in Norway. And this is what you get. So as the flow starts here, after a little while, you get all of this output voltage coming out of your device inside crude oil in these dynamic conditions. And hopefully next week we'll have some more news on this. So the last application that I'll talk about is on blue energy, and what we want to do is harvest wave energy to harvest wave energy from the ocean, but our peculiar study is to test it in relevant conditions. This is something that has not been done before, and that we found that decisive in what is happening. So blue energy for using triboelectrics is something that is something that is happening very quickly, and the applications of this is also are also very high. So you can put triboelectrics on a marine buoy and take advantage of the ocean waves to generate electrical energy for a different number of applications. So for the Internet of Underwater Things, that's something that is coming out now. For marine exploration or surveillance, or even for ocean cleanup systems. So the applications are huge. And if you want, you can read a recent review on this topic that is just coming out on energy and environmental science. What we did is that we wanted to assess how triboelectric nanogenerators work in actual sea states. So people typically use small testing setups and small waves to see what is going on, but these are not representative of the real conditions on the sea. And so we have installed 3 different triboelectric nanogenerators in an actual navigational buoy in a 1-to-8 model. And these three generators, they are based, all of them, on rolling spheres, just like in the case of the oil and gas. So the first, you have rolling spheres that come down a trench, and they strike a lateral structure here, and this lateral structure has 2 triboelectric materials. As they come together, they generate electrical energy. The second, which is, you can see here on this picture, is also based on these rolling spheres, but also on a trench. And this trench makes the spheres just moving on one direction. And as they move, the 2 materials that are on the bottom of the spheres, they come together and they generate energy. The third structure is this one. We call it anisotropic because the spheres can move in any of the 3 directions that are available in the buoy. So first, we have developed a testing system to simulate the wave motion, and this is it. So it's just a motor that rotates at a given velocity and a given frequency with the materials inside, and you can see there the spheres inside, and they are rolling on top of triboelectric materials. And this is what you get for the three devices that we have tested. So this is the unilateral. This is the lateral device, where you get voltages of about 15 volts. This is the trench that is unidirectional, and you get smaller voltages. And this is the anisotropic device where you have something like similar to the lateral one. And with that system that we have developed to assess the ocean conditions, we can fully access the voltage and the power and the current on different motion amplitudes and periods. So you can just change the amplitude of the motion and the period of the motion almost in a continuous way, and you can plot these 3D graphs for the different configurations that we have tested. And so this is the voltage, this here is the current, and this here is the power. And the 3, they behave more or less similarly. What you get is, as you increase the pitch amplitude, you increase the current and the voltage, okay? And as you decrease the period, you also increase the energy that you generate. This is all very nice, but this is just a testing system. So what we went, sorry, let me take out the pointer and put this. So what we went is to do a wave basins that exists in Porto, and where they can generate actual waves that are similar to the C states that you get more frequently. And this is the buoy. So this is a 1-to-8 model. Inside the buoy is the triballitic nanogenerator. Okay, and these are small period waves. You can see here the long period waves. This is the system that is generating. This is the system that is generating the waves. The waves come and the buoy moves according to the motion of the waves. And you see here that the motion of the buoy is something like this. So it rotates along the wave, it comes up, and then it goes down again in a very smooth way. This is the buoy. This is the wave basins that we have. This is the buoy, and these are 5 markers that are used to retrieve the motion of the buoy in the wave pool. So this system is similar to the one that people use on movies for with your green screen behind. This is the same similar, and it can gives you the 6 degrees of motions of a body. So this is the roll, the pitch, and the yaw. So the rotations. This is the surge, the sway, and the heave. So the linear motions of the actual buoy. And you see that the pitch, if you, sorry, we can go. Oh, sorry, this. Sorry, let me get back. This is my final slide. Okay, it's working now. So if you look here, the pitch is the motion at the y direction. The roll is the rotation at the x direction, and these are the 2 most important degrees of freedoms that you get out of a buoy. And here it confirms it's the one that varies the most is the pitch, and then the surge as the buoy moves also on the direction of the wave. So these are the results that we get out of all of these experiments. So we have varied the height of the wave, and we have varied the period of the wave. And as you increase the amplitude, is like this. You increase the energy that is generated by your devices, but on the period, as you decrease it, you get a maximum at the frequency of oscillation, the natural period of oscillation of the buoy. So the movement of the buoy and the movement of the triboelectric is coupled, and so you have to study dynamics of the 2 things together, and not just of the generated per se. And the device that showed the largest energy generation was again the lateral one and the anisotropic. But the most important thing to take out of here is that the lateral device is the one that generates the energy in the largest range of periods of motion. And this is critical because, for example, the C states buoys do not operate typically at their natural period. So typically the C waves have periods at this range and not at the ones that have the highest energy generation. So as a conclusion, I hope I showed you that triboelectric nanogenerators are a very promising energy harvesting technology that is appearing. That the output power increases with increase of the surface area, okay, and that you can change and engineer materials so that you can get higher output powers very easily. And then that there are a lot of applications that you can get out of this because they are extremely versatile. You can go into footwear, you can have something like flows water or of crude oils, and you can even use this in very extreme and harsh environments. But they are also very promising to be used in wave motion, but you have to properly measure them in actual sea states or actual sea conditions. So as my final slide, if it appears, it's taking too long. Sorry. Professor Panda asked me to show you a little bit of the opportunities that you can have to move and make research abroad. Okay. In Europe or in Portugal in particular. So there are just now an open call for European fellowship. This is the Marie Curie actions. They are very, very competitive, but also very interesting. And they allow researchers that have already a PhD to come to Europe, to any place in Europe, basically. So they are open now until the end of the week, I think. So it's not the best of timings, but they regularly open at least once or twice a year. So you should pay attention if you have a PhD and you want to come to Europe. This is a very nice opportunity. Then there are Erasmus Plus programs. Erasmus Plus is for undergraduate students, and they work very well especially for students that are in Europe and want to go to another university to do a semester or a full year. But there are also programs from this Erasmus Plus that allow people from all over the world to come. You just have to see if your university is in any of those programs, and if the university where you want to go is in this program. But if it is, then it's something that is very interesting, and it is fairly obtainable. So it's not very complicated to get one of these places. University of Porto in particular has this site where you can see the programs where it is involved. So if your university is involved with any university, with the University of Porto in any of these programs, you can contact them and see the opportunities for this. In Portugal, there are then two types of opportunities to come here and do research. So there are PhD grants that are given typically on a yearly basis. There is a PhD grant call every year from our funding funding institute, that is FCT. You have a site. The site is in English also, so you can just look it up. This is typically in March. But these grants are extremely competitive, and typically you have to have your degree already recognized by a Portuguese institution. But take a look at this. Then there is also a scientific employment stimulus. This is for postdocs, and they can go from early stage postdocs to already well-established researchers. This also opens typically once a year, and they are very, very interesting for people that want to come to Portugal. So this is just my thanks to a lot of people that have been working on this, either on our institute or outside our institute, on collaboration that we have. And I also thank you for attending this talk. Thank you.
Dr. Joao, there are not so many questions. There is one question by Pancham. Is the power generated enough for any practical applications?
It depends on the application that you want, but typically you use this to charge something. So you typically have a capacitor that is being charged, and then it's that capacitor that has enough power to a practical application. The most interesting application that I see now would be on wireless networks. So there are remote sites where you don't have power, and where you can have one of these generators just getting power from different sources, charging a capacitor, and then when needed, it discharges and sends an input signal with a sensor, with the sensing information. this is the application that I see that is most interesting at the short term.
Well, thank you. Before asking, I have one question about the higher study. So I just like to tell the participants, if you guys have any queries about the talk, please write in the chat box. Okay, Dr. Joao, just I'd like to ask one question about the higher studies. Is there a GRE or TOEFL is mandatory for a PhD?
Sorry?
GRE or TOEFL is mandatory for a PhD admission?
I couldn't understand the first part.
GRE, graduate research, I think engineering.
I'm sorry, but
just 1 minute. Just writing in your chat box.
Yeah, sure. I don't know what this is. Sorry.
Any mandatory qualification is not required, I think, right?
For the fellowship for a PhD grant,
yes.
What you have to have mandatory is a grade. So you have to be a master or finishing your degree, being that the master is preferred in terms of scores. Okay, so this is the mandatory thing that you have. But typically, nowadays you also have to have your master degree, for example, recognized by a Portuguese university.
Well, thank you. There is another few questions by Sikand Mudali. How are these devices used in implantable devices?
Yeah, well, this is not our study, but they have been used for different things, but particularly to take advantage of the heartbeat and to power pacemakers. Okay, so the question here is the encapsulation. So you have to encapsulate them if you use typical materials, or you can use biodegradable materials or biocompatible materials also. So there are different different materials that you can use depending on application. One interesting thing on these implantable devices is that you can use instead of just using the motion that is available inside your body, is that you can induce motion from the outside. So you can send waves that can activate your generator, and then this will be the power source for something inside, for example, for your pacemaker. That is the most interesting application.
There is another question. What is the process for material selection for TEN, tubular electron generator?
Okay, so the most important thing is to go through this table. So it really depends on what you want. Typically, you choose the ones that are most separated. So imagine if you have silica and Teflon. These are the two most separated. But now it depends on what you want. For example, you can use glass, but glass is extremely thick typically, so you don't have a lot of current coming out of this. Nylon is very interesting because you can have it in a foil and you can just purchase it and it's readily usable. But other materials like PMMA or PDMS, they are more convenient in terms of what you can do with them. So you can take PMMA, make dilutions of something, so make a surface texturization very easily. And so that is why typically people that want to change surfaces or want to dope these materials, they use this type of polymers. So PMMA, PDMS, Teflon, if you know how to make it. And so it really depends on exactly what you need for your application. If you want something that has only one electrode, you can use any metal, and this is better for you because it lowers your internal resistance. Depends on your application.
Yeah, thank you. I think it's good enough. Why there is another same question, same from Pancham. What is the use of PTFE field?
Yeah, so it's the same thing. So
what is the use?
Teflon is it's at the bottom of the series, so it's very negative because of the fluor that it has at the surface. So it's very negative, and you get the maximum output power possible on Teflon. You can also make it so you can purchase it on foils, and this is readily available. But there is also the possibility to make it in a simple way, so you can also use it for materials engineering purposes.
So is there any relation with the power?
Yeah, so it gets you the maximum power.
Okay, thank you. So I think there are no more questions. So with this, I think I like to thank Dr. Joao for
Thank you.
accepting our request and giving his talk. It's a very nice talk and a timely talk. So with this, I like to thank Dr. Joao and all the participants as well as my colleagues. Those are already helping me a lot to arrange this thing. So with this, I'd like to ask to Som sir to give some concluding remarks. Som sir, please.
Yeah, good evening. I'd like to thank the speaker, Professor Joao Ventura. That speaker gave a very good, some of the very good example, and then the application area is very interesting, seems to be very interesting. And at the end, he has given a very overview of how to apply for this higher study and research activities in their country, which is very huge. I think it will be very helpful for all the participants here, especially the students who are doing the PG program. So thank you, Professor Ventura, for our invitation and having this talk.
Thank you.
So I think we can conclude here, sir.
Okay.
Okay. Thank you, Professor Joao. Okay.
Thank you.
So next we will meet tomorrow. All of you meet at 4:30 p.m. Okay. So again, thank you, Professor Joao, and see you again.
See you.
Okay.